We have one more series of calculations to do using the glass beads as examples of soil as our three-phase porous media. The first thing we did was we determined the bulk density of these, looking at the mass of the solid material inside a given volume, total volume of soil. In this case, the beads represent the mass of the solid particles in the soil, and total volume is the 100 cubic centimeters to which I filled each of these graduated cylinders with the different sized beads. Then we took water, we added those to each cylinder and determined the volume, also weighed those. Then we poured the water back from the beads into the graduated cylinder and again took weights. Did that for each series. And what did we find? Well, we found that the ones with the largest pores and the ones with the smallest pores both had essentially the same porosity. So bigger and more doesn't fit together. One of those with the intermediate sized pores has the greatest porosity. One with somewhat smaller pores had greater porosity than the ones with the biggest or the smallest. What's it related to? It's connected. The porosity is connected to the bulk density, because as you decrease the bulk density, you're decreasing the volume of the solids that occupy a certain total volume, and thereby you're also decreasing the mass of the solids that occupy that volume. So at this point, let us finish these calculations rather quickly for what happens when we poured the water out of the graduated cylinders with the beads, and then took our masses again to see, okay, how much water is left in the beads once we've done that. So what is our water content, gravimetric, and then volumetric, and then the degree of saturation that we have, that we're going to use. So with that, let us continue, do these calculations. You've already seen all the definition versions of those. We'll just start here and do our mass values. So we need to figure out what the mass of the water is, and we'll put that in here. So we have the mass of the water in grams. Well, that's going to be 143.5 minus 142.8, so we end up with 0.7 grams. 114.3 minus 112.2, that should be 2.1 grams. 137.9 minus 134, that should be 3.9 grams. And then 157 minus 145.3, well, as I do my quick math, that would be 157 minus 145, that would be 12, but it's not completely, so this is 11.7 if I'm doing my quick mental math. Now I'm going to stop. I'm going to pause this for a moment and check my math. You might ask why I do those mental math things first. I don't want you to think I'm showing off, but what I'm trying to do is model for you a process. If you can do the mental math, the mental estimate first, then you know if that number that you get out of your calculator is in the right range. Because the most powerful tool you have is not your calculator, it's your brain. It's your ability to think and your ability to problem solve. So engage your brain first before you engage your finger and start punching numbers into your calculator. Now we've got a mass of water, so our next thing that we can do is the gravimetric water content. So we have that remembering that our formula for gravimetric water content, which is the water content by mass, is our mass of the solids divided by the, put the wrong thing here. It's the mass of the water divided by the mass of the solids with a precision of 0.01 grams per gram. With that, I'll do the example on the first one. Pause, put the rest of the data in. You should pause and do the math on your own. Make sure that you get the same answers. So for our first one, we have the water content by mass is equal, our mass of water for the first one is 0.7 grams. Our mass of the solids for that first one was 142.8 grams. So we do our math there really quickly. And we have 0.7 divided by 142.8. We get 0.005. So we get 0.0049 actually. Well, our precision is 0.01. This is one of those cases where I would probably go ahead and violate what I told you earlier. This number is not 0. So I would probably go ahead and round this one differently. I would do rounding twice, round from there to there and get 0.005, and then round up and get 0.01 grams per gram to maintain my precision. I'm going to pause, put in the rest of my values. You should pause. Use this pause to do your calculations. We'll come back in a moment. As always, check your values against these for the water content by mass, the gravimetric water content. Then we move on to the water content by volume, which is the volume of water relative to the total volume. Again, however, we cannot calculate it that way because we don't have the volume of the water. So even though this is the definition, we have to use a different way to calculate it, which we use the mass water content and the bulk density, divided that by the density of water. Our units and precision, 0.01 grams per gram. We have all the data now to do that. I'll do the first one. You can pause, do the others, and we'll come back. So we have the water content by mass, in this case for the first one, is 0.01. We're multiplying, and that's grams per gram. We're multiplying by the bulk density, that's 1.43 grams per cubic centimeter. We're dividing by the density of water, grams per cubic centimeter. All of our grams go away, and we get 1.43 times 0.01, and we're going to still end up with 0.01 cubic centimeters per cubic centimeter after we round, because we get 0.014. We round and we end up with 0.01. Now you do the others. We'll come back and check with you in a moment. Check your values there for your water content by volume. That leaves us with one more calculation to do, since we calculated the porosity on the previous example, we need to do the degree of saturation, which when we look, the degree of saturation, this is going to be expressed as a percentage. It is the amount of the pores that are filled with water. So by definition, we're looking at the total pore space and how much of that total pore space is filled with water. We don't know either of those things directly when we're working from the mass basis. And if we hadn't used graduated cylinders, we wouldn't have known what we were doing directly anyway. And when we get to soil, the pores are far too small for them to be filled. When we try and pour water in through a graduated cylinder, there would be way too much air that would be trapped in there to be able to make that estimate. So we're going to use the volumetric water content we calculated, and we're going to use the porosity that we calculated, multiplied by 100, so we get something in the percent. And so our precision to that is going to be percent to the nearest whole number. The nearest integer, which that means a whole number. So we're going to round to the nearest whole number. So what do we have? Well, for our first example, we have a volumetric water content of 0.01. We're dealing with cubic centimeters per cubic centimeter. We have a porosity of 0.46. We're going to multiply that whole thing by 100. In this case, all of our units are going to go away, and we're going to have an answer in percentage. And so, get our calculator out here. We have 0.01 divided by 0.46. It's going to be about 0.2, so 2%. So, since we're rounding to the nearest whole number, that is going to be 2%. So, I've got to write this out for this next step. I got 0.20217 multiplied by 100 is equal to 2.17%, but we're rounding to the nearest integer, so 2%. I've done this one. You do the others. Pause this one for a moment, do the others, and we'll come back together. So here's what we end up with, and let's just make a note of what's going on as we change from the largest particles, 25 millimeters, the largest spaces. Those hold the least amount of water per unit of volume, and in the biggest beads, the 25 millimeter ones, only 2% of the pore space is filled with water. When we go to the 10 millimeter beads, they're smaller. There's a lot more pore space, but only 3% of that pore space is filled with water, so the saturation percentage. Then we go to the 5 millimeter beads, 8% of the space there is filled with water, so after we poured the water back out, a significant amount of water remained in there. When we go to the smallest beads, those 1 millimeter beads, 27% of the pores in those beads are still filled with water. So that's what we see happens as we move to smaller and smaller particle sizes. Because those pores are smaller, you have greater capillarity that holds onto water. against the pull of gravity. And because the particles are smaller, they have more surface area, and water exists in surface area around the individual particles. In both of those cases, it increases the saturation percentage under a given set of conditions. In this case, our set of conditions was what we would call field capacity. Field capacity is that water left in the soil once gravity has drained what it can. And that requires you to remember something about those four forces that are working on that water drop. So if we have our water droplet in the soil, we've got the matrix potential that can pull several different directions, but that's the attraction of the soil solids and capillary pores. For the water. Gravity is always pulling down. Now, if we've got salts, the salts are going to pull on the water. But there has to be a gradient in the salt content in order for that to work. And the pressure is a push. So, in the condition where we've controlled all those things, in these glass beads, the only two forces that are at work in this particular case are our matrix potential that's holding water against the pull of gravity, that's determined in this case by our solids, the size of the beads and the size of the pores, because gravity pulls water from big pores, but it doesn't have enough energy to pull the water out of the small pores. So field capacity is a function of soil structure. With that, if you have questions on any of the calculations or on any of these thoughts, please contact me. Otherwise, have a great day, and you can work on these as many times as you need to make sure you understand.